Whilst line of business and product owners are focused on innovating around new use cases for generative AI, the challenge facing architects and builders is how do you host these workloads securely, reliably, and at scale? And how do you get these Gen AI-powered applications to market as quickly as possible in the most cost-efficient manner? Today, we're going to talk about how you can extend your existing investments in Amazon EKS to also support these generative AI workloads. My name is Vicky Whittingham, and I'm a containers specialist here at AWS. Today, we're going to talk about how Kubernetes has emerged as a platform on which you can run machine learning workloads. We're going to talk a little bit about the evolution of generative AI and the differences between Gen AI and machine learning. We're going to talk about how you can use Amazon EKS not just for inference, but for training as well. I'm thrilled to be joined today by David Charter from Unitary, who are going to explain how they've built an inference platform on top of Amazon EKS to process and analyze the content of millions of videos each and every day. We'll then wrap up with a few key takeaways. So let's talk about how Kubernetes has emerged as a platform on which you can run machine learning. Many organizations start with small-scale proof of concept, but at some point, you're going to need to scale out that workload to train on a much larger data set or to get some early feedback from your users. And we hear from customers that deploying these machine learning workloads can be really challenging. And the type of feedback we hear typically falls into around 5 different categories. The first of these is dependency management. Much machine learning model development begins from choosing a framework on which to build. Many of you will have heard of things like PyTorch. And these frameworks can come with lots of underlying dependencies that need to be managed. You're also going to need to be able to provision the vast amounts of compute and storage needed to train these models, and to have a way of managing this underlying infrastructure. You're often going to need integrations with other tools or systems to provide capabilities such as observability or identity access management at scale. You're also going to need to ensure that any security and compliance requirements you have are met. And finally, many organizations are looking for first-mover advantage in their industry. And that means that being able to get these machine learning models trained and in the hands of your users is really critical. And of course, it's impossible to talk about machine learning without considering cost, which is front and foremost of many people's minds. If you're running containers on Amazon EKS today, then those applications are going to be containerized. And containerization really solves that first challenge of dependency management. When you use containers, everything that your machine learning model needs to run is packaged into that single unit. So all of your code, configuration, framework dependencies, toolkits, everything you need is inside that single object. And what that really allows you to do is move that object very consistently between different environments. It's relatively straightforward to share your training scripts through version control. But what's much harder is to collaborate with other users and guarantee the reproducibility of those results without sharing your underlying execution environment. And that's really where containers fit into the picture. But containerization only really solves part of that challenge. To resolve things like provisioning the vast amounts of compute and different integrations that you need something beyond just containerization. And that's where container orchestrators like Kubernetes come into the picture. Many organizations choose Kubernetes because it's highly scalable. It's possible to scale on 2 different dimensions: to control how many replicas of a given pod you need to run, and also to scale the underlying infrastructure to provide just the right amount of compute that your workloads need to run. It's possible to achieve improved resource utilization with Kubernetes, as you're able to define at a really granular level exactly how many resources a particular container needs to run, and let Kubernetes take care of scheduling that workload in the most efficient manner. Kubernetes also allows you to standardize across your organization. You can use a consistent set of operating procedures and tooling, regardless of the type of workload that you're running. And finally, the open source community. Kubernetes is backed by a vibrant ecosystem of different people collaborating, not just on the core Kubernetes project, but also to provide tooling for specific use cases, such as machine learning. I just wanted to dive a little bit deeper into this concept of standardizing on Kubernetes and what that really means. Many organizations that I work with have chosen Kubernetes as a common interface to manage deployments in the cloud, on-premise, and at the edge. And many organizations have invested in building platforms surrounding Kubernetes that manage the underlying compute, storage, and networking primitives, building generalized capabilities for things like observability, build and release automation, taking that even further to really empower your developers with an efficient set of tooling to help them do their jobs, things like audit and logging for them to consume. And for many organizations, this exists in production today and is running existing, more traditional workloads. And so it can feel like a really natural evolution to simply extend the capabilities of your existing platform to also run these machine learning workloads. So where does Kubernetes fit into the overall machine learning lifecycle? Typically, it's when a data scientist is finished with local experimentation. Maybe they need to scale out to train on a much larger data set. Or they've got too many versions of a training script, and running them all locally is becoming a bottleneck. So what you can do is you can tell Kubernetes, this is my container, and these are the resources that it needs to run. You can define the CPU, GPU, and memory requirements, and let Kubernetes take care of provisioning the underlying compute on which those containers will run, pulling your image from your chosen container registry and scheduling that onto one of your nodes. And what this really provides you is effective orchestration for machine learning. Kubernetes will monitor the state of your running workloads and try to ensure that they're always reconciled to the state that you've defined. And what this gives you is the ability to automatically recover and self-heal from any failures. And so that brings us to why we've seen many organizations choose to build machine learning workloads on top of Kubernetes. Before we talk about Amazon EKS in a bit more detail, I just wanted to do a quick overview of generative AI. And in everyday conversation, I think we all hear the terms AI, Gen AI, machine learning, deep learning, all thrown about and potentially even used interchangeably. But there are subtle differences between the four terms. So if we start at the top with artificial intelligence, this is really about the ability for a computer to mimic human intelligence. We then have machine learning, which is really all about taking vast amounts of data and analyzing that data for patterns which can then be used to predict outcomes in new or unknown situations. We then have deep learning, a subset of machine learning, which uses specific algorithmic constructs called neural networks, inspired by the human brain. And finally, we come to generative AI, the ability to generate new and original content. And Gen AI has really captured all of our imaginations over the last couple of years for its ability to write stories, produce videos, music, and even code. Many organizations have been innovating with machine learning for many years now. But there are really three key innovations that have led to the explosion of generative AI that we've observed in recent times. Firstly, the vast proliferation of data. Thousands and thousands of terabytes of data are produced every single second. And what this provides is a vast amount of material on which to train these generative AI applications. Next, you have the ability of cloud computing, the ability to spin up clusters of hundreds or even thousands of GPUs without requiring upfront investment in your own hardware. And finally, innovations in specific machine learning techniques, such as the transformer-based neural network architecture. And this has really allowed us to build models with many more parameters than was possible before. I think we're really just at the tip of the iceberg in terms of the use cases that we'll see organizations eventually using for generative AI. But some of the common themes we see today are things like looking at how you can enhance your customer experience. And the most common or obvious example here is chatbots. Now, chatbots aren't necessarily new. They've existed for a few years now, but they're often rule-based, hard to maintain, and cannot feel very conversational. With Gen AI-powered chatbots, it's possible to achieve a really high level of personalization and customization that can make those conversations feel much more realistic. Next, we have around boosting employee productivity, an area that I'm personally very excited for. Imagine a world where you had your own Gen AI assistant able to scan through all of your messages, emails, news articles you need to be aware of, and provide summaries, even alerting you to the time-critical activities that need your attention. If you're a developer, being able to use generative AI to write some of that boilerplate code and let you focus on writing the most interesting new features. And finally, improving business processes, things here like document processing and data augmentation. The last thing to mention here is just about the differences between traditional machine learning models and those used for generative AI. With traditional machine learning models, you're typically needing to process large amounts of data and prepare that with labeling to then train that machine learning model for a very specific use case. With foundational models, what you're doing is providing a large amount of unlabeled data, essentially raw data on which you're able to train these models. And these foundational models have a wide applicability to different tasks. And what you can then do is you can then customize those models using a much smaller set of data compared to more traditional machine learning methodologies to then really fine-tune those models for your specific use case. And what this also means is you don't necessarily need to start from scratch each and every time you come up with a new use case for generative AI. So we're now going to talk a little bit about how you can use Amazon EKS for both inference and training. Amazon EKS provides you the open flexibility of Kubernetes, coupled with the security and resiliency of an Amazon managed service. Whilst many of the challenges that we discussed earlier for machine learning are still broadly applicable to generative AI, the differences between those traditional machine learning models and these generative AI models can lead to some additional considerations. First of all, scaling. Scaling can be even more pronounced for these generative AI models because of the vast amount of data they need in order to be trained. And linked to this, it's unlikely that these models will fit onto a single instance. And so what many organizations choose to do is to distribute that training across lots of different nodes. When you're running distributed training in this fashion, you need to be able to identify and remediate any failures. Amazon EKS's approach to supporting this large-scale distributed training is typically around providing seamless integration to the underlying compute, network, and storage primitives. For example, on the compute side, we've spoken a lot about needing to scale your underlying compute, that is where your training jobs are going to run. But as the size of your cluster increases, you're also going to need to manage the control plane, that is the brain of the cluster. And when you use Amazon EKS, we take care of auto-scaling the control plane in the background for you. Again, if you use EKS today, you're likely to be familiar with the EKS optimized AMIs that we produce. And we also have versions of these optimized AMIs specific for accelerated instance types that work out of the box with things like our NVIDIA or Trainium-based instances. We also have AWS deep learning containers that you can find in ECR, pre-configured and built with popular deep learning frameworks. On the storage side, our focus is typically around providing CSI drivers or container storage interface drivers to allow you to interface with the various AWS storage services for your cluster. Things like EFS, FSX for Lustre, or recently last year, the S3 CSI driver. And then on the networking side, providing device plugins that allow you to use elastic fabric adapters within your Kubernetes cluster. EFA provides a specific EC2 network interface that's designed for low latency, high bandwidth, inter-node communication. And what this can really do is speed up the time it takes your inference jobs to complete. Now, on the inferencing side, once you've trained a model and you're happy with the performance of that model, you're going to want to serve it to your users for them to interact with. And scaling is still a challenge here. But what you're really going to want to scale on is the number of inference requests that you have pending. What I see a lot of organizations doing here is to choose to scale based on queue length. And that's something that David's going to talk about in just a few moments at Unitree. Performance is now a concern because, with inference, this could be in the path of your end users. And you don't want a slow prediction to ruin a great customer experience, especially if your GenAI-powered applications are being used to enhance customer experiences or run critical business processes. And finally, cost. Once you have a relatively successful model, you may not want to retrain that as frequently, and so a large proportion of your cost can eventually come from inference. One tool we see being adopted for inference workloads is Carpenter. Carpenter is a high-performance compute provisioner for Kubernetes, and it allows seamless auto-scaling of your data plane. With Carpenter, you don't need to define node groups for different instance types, sizes, availability zones, or compute options. Instead, you provide Carpenter with a set of constraints as broad or as narrow as you like, and let Carpenter determine the best and most appropriate instance type to provision. Carpenter will take a look at the aggregate resource requirements of any pending pods that you have, and use this to provision just the right size node for those workloads in order to drive up overall cluster utilization. And finally, Carpenter is open source and native to Kubernetes. We actually donated Carpenter to the Kubernetes auto-scaling special interest group earlier in the year. David is also going to talk about Carpenter in just a few minutes. And actually, if you wanted to learn more about Carpenter, directly after this session in the next theatre across is a session with Monzo, explaining how they've optimized their Kubernetes deployment on Amazon EKS using Carpenter and EC2 Spot. When we talk about customers who are running generative AI workloads on EKS today, they typically fall into three distinct use cases. First of all, you have organizations who are building their own generative AI platforms on top of Amazon EKS to provide services for other users to train and infer their own generative AI applications. At the next layer, we have customers who are building foundational models, such as Anthropic, who produce the Claude family of models, or Runway, who produce Stable Diffusion. And finally, at the top, we have customers who are focused on building consumer-faced generative AI applications, such as Adobe, who spoke with us last year at reInvent to talk about how they've extended their existing EKS platform to also support GenAI workloads in the form of Firefly. With that, I'd love to hand over to David to tell you more about how they approach inference at Unitary.
Hi, my name is David, and I'm a platform engineer at Unitary. Over the next roughly 10 minutes, you will discover how we've managed to achieve some really surprisingly big things with a small team. Unitary is a startup which makes the internet a safer place by building and deploying AI models to detect harmful content and to keep platforms safe. Existing AI tools for content moderation are not good enough, leading to a massive reliance on human moderators. But human moderation doesn't scale, so something needs to change. The industry standard for object recognition fails in two key ways. Firstly, it doesn't take context into account. For example, you may be posting about your favorite spy thriller, which is not the same as someone than a gun being used in a video in a real fight. Secondly, it doesn't consider all signals together. The same image could mean different things with a different caption. The first, about your dinner plans, the other promoting drugs. At Unitary, we use context-driven models that take into account multiple signals, whether that's text, audio, or visual, to classify online content. Our engineering team both train our own machine learning models and make them available to our customers. Our machine learning engineers will take our trained models and store their outputs ready for deployment, as well as identifying open source models that can be fine-tuned to support our own trained models. However, what we'll be talking about today is what my team is responsible for. How do we take these models and build a platform that make them available for classification for our customers? My team's mission is to build a cost-efficient inference platform capable of classifying the content of millions of videos and images per day. We identified several key requirements. Millions of hours of video are uploaded to the internet every day. And so we knew for our first milestone, we needed to cover a small portion of this, which would be billions of video frames or images every single day. So being able to operate at scale is really important. But also, we needed to design our platform to scale as we grow. Customer traffic is always unpredictable. And we need our platform to have the flexibility to adapt to whatever we get sent. We could have several videos, several thousand videos sent all in one go, or periods of time where no content is sent at all. Our customers want to make decisions as quickly as possible. And so we need to be able to balance between a low enough latency whilst also maintaining the flexibility to adapt to everything they send to us. And how can we achieve all of this as cost efficiently as possible, especially as a startup? There are a variety of ways in which you can make models available as a service. We chose Kubernetes for a lot of the reasons that Vicky mentioned, but in particular, because it can adapt and scale as we need. It also has a load of open source tooling that we can utilize. Our customers send content to an API. This content is usually a media file, whether that's an image or video, which gets accepted by a load balance ingress layer, and it is queued for processing. At the next stage, we need to prepare the content so that it can be classified by our models. For videos, this involves breaking up the different video frames and extracting the audio. On each video frame or image, we run several models, and we have 3 microservices which achieve this, each with a different set of models. Once processed, we then queue the results ready to send back to our customers via a webhook and to store the results in the database. One of our key architectural design decisions was to make our platform event-driven. We knew that we would not be able to predict what our customer traffic would be like, and we only have finite resources. We considered several different message brokers for our queues, but settled on SNS plus SQS because of the simplicity it gave us when we were already using AWS, and the fact that we know that scaling is managed for us. All of our processing runs on pods in EKS, including all of our inference processing. One of our key components here is the NVIDIA Triton Inference Server, which is an open source and containerized way to serve models. We found it to be amongst the fastest and most robust on the market. I'll be discussing the optimizations of this component in more detail later. So when we chose to use Kubernetes, we went straight for EKS, as we're a small team, and so we don't have the time or resources to self-manage Kubernetes. Instead, our engineers can focus on delivering value for our customers rather than managing or diagnosing clusters. This gives us great cost efficiency benefits. Plus, we can trust AWS to give us the support and resilience we need for our platform to be successful. As a small team, we need to automate as much as possible. One of these areas is the automatic scaling of our clusters. Our event-driven architecture is ideal here, as we can react quickly. As queues build up, we can scale up. However, as part of this, we don't want our clusters to be in a constant flux of scaling up and down. And so we had to spend time optimizing our logic so that we can balance between reactivity and stability. Auto-scaling means that we provision and pay for the resources that we're actually using our exact need at that exact time. There are two parts of our cluster that we auto-scale. At the application level, we use CADA, which manages the number of pod replicas. CADA is a CNCF graduate project, which addresses some of the limitations of the horizontal pod autoscaler. In particular, for event-driven systems, the resource required does not always match the application need. Instead of just CPU or memory usage, CADA uses event-driven metrics to determine how many replicas it requires. In our case, we use the lengths of our SQS queues. And when the number of replicas exceeds the amount of compute we have available to us, we turn to Carpenter in order to find us EC2 capacity that we can use for our Kubernetes nodes. Now, we are a bit of a special case. Kubernetes nodes, you might expect to have multiple pods, but our inference pods require a whole GPU, which means that we are often scaling nodes every time that we need to increase the number of increase our inference traffic. We chose Carpenter because we knew we needed to scale really quickly, and it was faster than other options that we considered. As well as for the scaling up and down of our clusters, we also use Carpenter for cluster consolidation. This allows us to move pods to utilize cheaper nodes. This feature proves very useful for our next cost efficiency strategy of preferentially using Spot. Spot is spare capacity, which has a significant discount compared to on-demand instances. However, by their very nature, these Spot instances can be interrupted. And so we've had to build tolerance into our platform for this. We are constantly monitoring for interruption signals. And then when we receive those, our pods gracefully shut down. Our event-driven architecture also helps here, as our separate processing parts are all isolated. We again use Carpenter to adapt to Spot availability. When Spot availability is high, we're able to move our nodes onto Spot instances. And when our nodes get Spot interrupted, we can move those pods back onto on-demand instances. As a result of these optimizations, we've been able to do quite a surprising thing, which is run 100% of our back-end processing on Spot instances for over 30 days. This includes hundreds of GPUs. Now, in order to achieve this, there was another hurdle we had to overcome, which was the startup time for our inference pods. We want to be able to react quickly and be Spot tolerant, but the Spot interruption notification is only 2 minutes prior to the node being taken away from you. During this time, Carpenter drains and provisions a new node. Now, as a reminder, one inference pod has to have a whole GPU, so it's a whole node. So when a Spot interruption occurs, we need to move that pod. We observed that it can take 10 minutes for a new pod to start up after the previous node has been interrupted. This proves a challenge, as our new pods are still starting up several minutes after the old pods have been deprovisioned. This interrupts our throughput. So why is this so long? Machine learning containers are often very big. As I mentioned earlier, we use the NVIDIA Triton Inference Server, which is made up of model execution backends, software dependencies, and the code used to run and serve the models. We observed that most of the time when a pod is starting up was spent downloading the image from the Elastic Container Registry, from ECR. So one strategy here could be to make the image smaller. We were able to do this by removing model execution backends that we weren't using. We also were able to convert some of our models so that they can use a single model execution backend. This meant that we could drop unused model execution backends and make our image smaller. So as a result of this, we now have a smaller Triton container image, which has been optimized for our models. We paired this with using a BottleRocket AMI, which uses a lightweight Linux operating system for really fast boot times. We use this because we don't want the node startup time to be part of the problem. However, even after all of this, it was still taking several minutes for a new pod to start up. So we had to do something else. What we did was we cached the container image at the node level in the EBS volume. Now, this introduces I/O latency, however, from when you need to restore your EBS volume from a snapshot. So the final piece of our puzzle was fast snapshot restore, which makes sure that the EBS snapshot is always warm and ready to be used. As a result of all these optimizations, we are now in a position where we can provision and start up a new inference pod within 2 minutes. So we can now provision nodes, new nodes really quickly. But we had another challenge. In order to reach the peak inference rate that was required to process millions of hours of video every day, we were having to run very large EKS clusters, including hundreds of GPUs. Each of these pods are emitting logs and metrics, which makes observability really hard at scale. How we solved this was using AWS managed services. This allows us to get the industry standard tools such as Prometheus and Grafana without the stress of having to manage and operate them. We just had to look after the Prometheus pod used for scraping. And like some of our other components, we use the vertical pod autoscaler so that the amount of resources it has is able to scale with the cluster size as the logs and metrics increase. We were quite excited when AWS announced the Managed Prometheus Collector, which allowed us to offload that scaling back to AWS and also the management of scraper config. This is an example of how we have had to continue to evolve and change our architecture. We have no strong attachment to one particular tool. We're always ready to swap for one that works better at scale. So I've given you a small glimpse into the journey we've had at Unitary. And we've learned a lot along the way. In particular, we need to have high tolerance to unpredictability, whether that's spot interruptions or unpredictable customer traffic. We also choose to run only what we need, and we have fast scaling of streamlined services in order to maintain a high throughput. And we discovered that when you automate as much as possible, you can often leave your platform to it with reliable monitoring for when things go wrong. But this is not the end. We are going to need to continue to push the boundaries of scale in order to classify more of the internet. This is likely to lead us to GPU availability challenges, as GPUs are a finite resource, and there's a lot of competition. So we're going to need to build logic so that we can rebalance our cluster and utilize the GPU availability in multiple AWS regions. A lot of what we've focused on so far was the scale aspect. And now we want to maintain low latency at this scale. We want to have faster and smarter auto-scaling in order to achieve that. So, as the content upload to the internet increases, we are going to continue leveraging EKS that will scale with us in our goal to make the internet safer in order to improve lives and create a fairer world. Back to you, Vicky.
So we've spoken today about the challenges of running machine learning, the differences between machine learning and generative AI workloads, and how you can use Amazon EKS, not just for training, but also for inference. And perhaps understandably, we focused a lot about the infrastructure layer. And so some of you may be wondering, well, what about at the application layer? And here, one of the main challenges with Kubernetes is that data scientists are not necessarily Kubernetes experts. And Kubernetes constructs, such as stateful sets or deployments, can be unfamiliar. So how do we solve this? What I see many organizations doing is using EKS for what EKS is good at, and that is managing the underlying storage, compute, and networking primitives. And then many organizations choose to utilize the extensive open source tooling available to provision more advanced machine learning specific capabilities. And what this really does is it provides a level of abstraction for your data scientists to abstract away some of the underlying implementation detail of using Kubernetes. This is a trend that we see for more traditional application development as well, with many organizations investing in things like internal developer platforms to, again, remove some of that complexity of Kubernetes and allow your developers or data scientists to really focus on the job at hand. And there are many such tools available as part of the Kubernetes ecosystem to run generative AI or machine learning workloads on top of Kubernetes. One example that we've created here at AWS is called the JARC stack. The JARC stack provisions 3 open source tools on top of an EKS cluster to provide end-to-end machine learning orchestration capabilities. The JARC stack includes things like Jupyter Hub, which provides a familiar interface for your data scientists who are often used to using things like Jupyter Notebooks for model experimentation and development. You've then got Argo to orchestrate parallel jobs, and Ray or RayServe to provide online inference APIs for users to interact with. This QR code will take you through to a blog that we've written about the JARC stack. There, you'll find a Terraform blueprint that you can use to provision these 3 tools on top of an EKS cluster, and a tutorial that walks you through how to fine-tune a stable diffusion model on Amazon EKS and serve an endpoint to users for text-to-image generation. So check that out if that sounds interesting. This is a high-level architecture diagram of the JARC stack. On the left-hand side, you'll see all of the different Kubernetes add-ons and operators needed to provision and maintain this toolset. You've got things like the GPU plugin to give Kubernetes visibility of the underlying GPU hardware. You've got things like the AWS load balancer controller to provision the 2 load balancers you can see at the top. You've then got 2 entry points into the cluster. First, for your data scientists to be able to interact with those Jupyter notebooks running on nodes within your Kubernetes cluster. And on the right-hand side, you've got a load balancer through which end users can submit inference requests, which will ultimately be scheduled onto a Ray worker node in order to generate those results. And you'll see that only the workloads that need to run on GPU instances are running on GPU instances, with the more foundational capabilities needed to make the cluster operate running on CPU instances. We've spoken today a lot about generative AI and machine learning, But over the last few years, we've really seen an increase in the number of customers wanting to run data workloads on EKS. And so to support that, we've created the Data on EKS project. This QR code will link through to our website. And the main aim of this project is really to make it easier to build data platforms on top of Amazon EKS, not just for workloads like GenAI, but also for data streaming and data analytics. Here you'll find things like Terraform blueprints to help you provision popular open source tools, performance benchmark reports, and even some best practices. So I just want to leave you with a couple of takeaways from today's session. First of all, you can extend the foundational capabilities of your existing EKS implementations to support these generative AI workloads. Doing that means you're not starting from scratch. You're building on something that already exists, and that can help you reduce development time and therefore cost, and really accelerate that time to market. You can let Amazon EKS take care of scaling the control plane on your behalf and use tools such as Carpenter to provision the vast amounts of compute needed for training and inference workloads. And finally, you can check out the Data on EKS project for some examples and inspiration of how to get started. The last thing I wanted to mention today is Skill Builder. With Skill Builder, you get access to over 600 free different training courses that you can use to learn at your own pace and focus on the topics that you care most about. Something we added to Skill Builder at the end of last year is the EKS Knowledge Badge, which aims to give you a broad understanding of core Kubernetes concepts with a focus on Amazon EKS. You can test and certify your own knowledge or even just learn more about a specific area that you're interested in. With that, we've come to the end of the session. If you can just take a few seconds to leave us some feedback by scanning the QR code on the screen, we really love to make these sessions even better going forward. Thank you to David for being with us today and sharing your story at Unitree. Our LinkedIn details are on the screen, so please feel free to reach out or come and have a quick chat with us now if you want to find out more.